This recording is going to cover the endocrine function of the pancreas. Now, the pancreas is both an endocrine as well as an exocrine gland. So I do want to mention the exocrine function of the pancreas. The majority of the cells that you find in the pancreas are what are referred to as acinar cells or pancreatic acini, which you see here. Those cells produce digestive enzymes. So we'll be discussing those when we discuss the digestive system. But what we're going to be talking about today are the islets of Langerhans, or the pancreatic islets, the little lighter stained regions that you see when you look at the pancreas under the microscope. We're specifically going to be looking at the role of insulin and glucagon, and the cells that will be producing those, we'll be looking at the beta and alpha cells, and we'll specifically tell you which cell makes what hormone. So those are the ones that we're going to primarily discuss. So we're going to start with insulin. Now, insulin is considered to be a major anabolic hormone. So if it's involved in anabolism, we're talking about building, growing, synthesis type reactions. And we're going to be looking at, so when we go through the various functions, you're going to see that. Now, the cells that produce insulin are the beta cells. So the beta cells of the islets of Langerhans. People with type 1 diabetes mellitus the beta cells have been destroyed, therefore they don't produce insulin, just so you're aware of that. Now, insulin, the major stimulus for its secretion is elevated blood glucose levels. That is the major stimulus for it. There, you'll see on this picture, there'll be something else that stimulates it, but you'll see the higher levels of insulin are going to be released when blood glucose levels are elevated. So if you look at the picture from a biochemistry textbook, the scenario was they had an animal ingest a straight glucose meal. That's all that they took in. You'll notice initially the blood glucose levels go up, but then you see they start to decline is because of that stimulated the release of insulin. And insulin's job is to get the blood glucose levels back down, and we're going to look at how it does that. You'll notice over here is if an animal consumed just a straight protein meal. Glucose isn't going to be changed because when you break down proteins, you're just going to get amino acids. You won't get glucose. What you'll notice is there will be a slight increase in insulin, but if you look at the numbers, it's nowhere near the amount that you get if you have elevated blood glucose. Now, the reason why a protein intake will also increase insulin, but not quite as much, is because, again, insulin is an anabolic hormone. One of the things that's involved is protein synthesis, and you use amino acids to make proteins. But you'll notice the largest amount of insulin is released if you have elevated blood glucose levels. So let's look at some of the effects of insulin on target organs. So we're going to start first with the liver. Okay, so here is the liver. So what it does in the liver, it increases glucose uptake just because you've got just elevated glucose levels, and the receptor it has to be able to transport glucose in it is going to just allow, just because you have a lot more glucose in the bloodstream, you're just going to take it up more. And what it does is it increases glucose uptake, it increases its use. And we'll show you what we use it for. So it will increase glycogen synthesis. So we'll store away that glucose for later. So in between meals, then we can break down glycogen to get glucose, but here we're just going to store it up. It also will increase the synthesis of fat. It also, I say increases use, we're going to use it to make things. So these are, you'll notice, these are anabolic reactions. But we'll also, since you've got glucose around, if we've got a little excess glucose, we'll use it for energy. So you'll have an increase use of glucose for energy, which is glycolysis. So that actually is a catabolic reaction, but that's where you got plenty of glucose, we'll just use it for energy. Any excess, we'll store it away as either glycogen or fat. Now in skeletal muscle, so this is skeletal muscle here, what it will do is it will, I'm going to change the color so you know. Okay, so we're doing this in green. It will increase glucose uptake. And the way it does it here is there's different glucose receptors, or I should say glucose transporters. In muscle, we have what we refer to as GLUT4 transporters. And insulin will increase the number of GLUT4 transporters. What these transporters do is they transport this hydrophilic substance, such as glucose, across the membrane. So we have more of these receptors, we can increase the glucose uptake. The glucose will then be used for making glycogen. So you have a lot of glycogen storage in muscle as well as liver. So we have glycogen synthesis. This glycogen, though, in muscle will only be used for itself. So muscle will break down glycogen to glucose to use for energy for muscle contraction. It will never be released into the bloodstream. They have the inability to release the glucose back in the bloodstream, so it's only going to be used for energy during, say, exercise. Another thing insulin will do will increase protein synthesis. So again, you'll see it is an anabolic hormone. Okay? Now the last one we're going to look at, we'll do it in gray, is adipose tissue or fat. So in here, again, think you've been fed. And when you think insulin, what you think you've been fed. So we've been fed, we've got plenty of glucose around, so we're going to, again, increase glucose uptake, because again, you need a glucose transporter to get glucose across cell membranes, and it does it via increasing GLUT4 transporters. GLUT4 transporters are not found in the liver. They have a different type of glucose transporter. It will also increase fat synthesis, which is lipogenesis. So those are some of the major effects of insulin. So overall, you've been fed, use the glucose for energy. So adipose tissue can also, I should say, increase glycolysis. Muscle, I should have put also increased glycolysis. Use that glucose for energy, but any excess, what we're going to do is we're going to make glycogen in the liver and the muscle. We'll increase fat synthesis in the liver and that fat will then be transported out into the bloodstream and then sent to different tissues to either use for energy or to fat for storage. And we're going to increase lipogenesis in adipose tissue. Okay, so those are the major effects of insulin. Now, if we look at glucagon, glucagon is a major catabolic hormone. Glucagon is considered to be antagonistic to insulin. It has opposite effects as insulin has. So this is overall breaking things down. When you think glucagon, I want you to think you haven't been fed, glucose is gone, think glucose levels are low. So what we need, though, is like if you haven't been fed, you still need energy to be able to maintain homeostasis. So what we need to do is we need to enable certain pathways so we can get blood glucose levels to an adequate level, but also supplying energy, some sort of energy for tissues to use. So the cells, though, that make glucagon are alpha cells, and just remember the A is like you see in glucagon. So alpha cells are the ones that produce and secrete glucagon. Now the major stimulus for glucagon is, again, think of it's the opposite of insulin. The major stimulus is low blood glucose levels. Other thing, though, that will stimulate glucagon is high intensity exercise. So if you look here, similar to when we looked at insulin, is they gave an animal glucose and they're looking at glucagon levels as well as glucose levels. So again, you have straight glucose, glucose levels are going to go up. But here, what you'll notice overall is glucagon levels are going down because you have plenty of glucose, you don't need glucagon. What you're going to need is insulin. But here, if you ingest a straight protein meal, you'll notice that glucagon levels increase. So if you have protein, you're not taking in glucose, and you always need to maintain proper levels of glucose levels. I just kind of repeated myself. And adequate levels of glucose in your blood all the time, because some tissues have a heavier requirement for glucose, like the brain. Red blood cells can only use that for energy. So the thing is, we're like, well, we're going to need some glucagon because we're not getting it from what we're eating. So we're going to need to secrete glucagon. We're going to show you what's going to happen as a result of glucagon in the bloodstream, its major effects on target organs. So you'll see here, let's just look at this one right now. Skeletal muscle, there's no effect because there is no receptor for glucagon. Okay, so even though blood glucose levels are low, we can't target the skeletal muscle. But I had mentioned when we were talking about insulin is the skeletal muscle cannot release glucose into the bloodstream. It's only used for itself, so it doesn't really matter because it's not going to help us. But if we look at the liver, the major effects on the liver is it's going to increase the breakdown of glycogen or glycogenolysis, so we can have some glucose out into the bloodstream. It will also increase gluconeogenesis, so the formation of new glucose. We're also going to increase the use of fat for energy. So liver can use fat for energy. It doesn't want to use glucose because it wants to make sure other tissues can use the glucose, the ones that have a higher dependence upon it. So actually I'll put decrease glucose usage. Now, gluconeogenesis is where you're forming glucose from technically a non-carbohydrate precursor. It requires a lot of energy to do that. And where we're going to get the energy is from fat. So in adipose tissue, you have increased breakdown of fat or lipolysis. The fatty acids will be used by various organs for energy because I had also said glucagon is released when you have not been fed. You're still going to need energy, so we're going to rely on fat for energy. That fat, the fatty acids, will also be used for energy from the liver in order to synthesize glucose. The glucose can be synthesized from that glycerol backbone and triglycerides that are in fat. It can be used things such as lactate or lactic acid too. So glucagon is overall more of a catabolic hormone. So I want you to think about why some people would rely on more of a low carbohydrate intake and more higher protein intake to try to promote weight loss. So we're going to stimulate glucagon levels, which helps to increase fat breakdown. But overall, the things that are set in motion is because we need to still maintain blood glucose levels, and since we're taking such a low carbohydrate intake, we need more glucagon around. So this is the last bit of the recording about the endocrine effects of the pancreas.